Hello everyone, this is Oluwaseun Martins, and in this video we'll be discussing introduction to sensors and transducers. This is the chapter 1 of the course, Mechatronic System Design 2. So here we'll be talking about sensors and transducers and other related topics. So the first thing we'll be looking at are sensors. So a sensor itself is an element in mechatronics or measurement system that detects the magnitude of a physical parameter and changes it into a signal that can be processed by the system. So what are we saying here? We are saying that a sensor is just an element, that can detect the magnitude of a physical parameter. The physical parameter here can be either temperature, can be pressure, can be soil moisture content, can be the weight, of a certain article, using a load cell as a sensor in that case, So the sensor detects the magnitude of that physical parameter, and it goes on to change that detected magnitude into a signal that can be processed by the system. And the reason for that is this. Every sensor requires a microcontroller to read from it. And the microcontroller, in this case, only understands changes in either voltage level or current level. So what the sensor does is that when it detects the magnitude of the physical parameter, it changes that detection into an equivalent change in voltage level from its own output to the microcontroller, or current output from itself to the microcontroller. So the microcontroller now can read that voltage or current level to say, okay, this is the magnitude of what has been detected by the sensor. Now, the active element in every sensor is what we call a transducer. And even in some cases, you see the word sensor and transducer used interchangeably or used together, the way we have made the topic look in this case. So for every system that has to do with monitoring and control, for any system to be able to monitor and control, you need sensors to measure physical quantity or quantities such as position, distance, force, strain, temperature, vibration, and acceleration. Now, one thing is this monitoring and control system. You can't have a system that control without monitoring, but you can have a system that only monitors and not control. But whenever you have a system that controls, that system must have monitored. So monitoring and control system, that's just a brief explanation of that. Now we have several types of sensors. We have proximity sensor, you have the infrared sensor, you have light sensors, color sensor, you have load cell to determine the weight of any article, you have temperature sensor, pressure sensor, we have force sensor, we have tilt sensors, which are being used in robotics. We have even cameras as sensors, in some cases. We have encoders, to determine the revolution of a certain object. Several types of sensors that you can have. But what will determine the kind of sensors you use in any application is what you want to actually measure, what you want to detect will determine the kind of sensors you would apply in that case. Now, in the design of sensors and transducer, their design always involve the application of some law or principle of physics or chemistry that relates the quantity of interest to some measurable events. What we're saying here is that sensors and transducers require law or principle of physics or chemistry that relates whatever it is that is to be measured, to some measurable event. If you take temperature, for example, now, I want to measure temperature. So in the design of a temperature sensor, they have used some law of physics and chemistry, or law of physics or chemistry, that can relate temperature, to change in voltage, or change in current. So that is what that is all about. And practically every transducer in every sensor, applies one or more of these principles in its operation. So the level of automation and complexity of any control system, when you have a control system, the level of complexity and automation of that control system can be determined by the extent to which sensors and transducers are used, on that very control system. So the more sensors and transducers you have on a control system, that tells you the level of automation or complexity of that very control system. And these days, we can have sensors, so small by just the dimension of 0.5 by 0.5 mm. And why we need to have sensors on chips, this miniaturized, is because the modeling requirements of complex control systems, have introduced the need for fast, sensitive, and more precise measuring devices. And due to that, demand for sensors is on the increase, and also the demand for them to be miniaturized so that they can be implemented on a very micro scale by combining several sensors into a single unit have also increased because of the need for increase in the design of complex control systems. So that has increased the need for sensors to be more miniaturized, and even the combination of 2 or 3 or more sensors on a single chip, which is probably as small as 0.5 by 0.5 mm. So the selection of sensors or a transducer, depends on some factors. Number one, like I've explained earlier, is the variable or the variables measured and application, what you want to measure or the application you want to use such sensor for. Now, the nature of the precision and the sensitivity required for the measurement, because every sensor also have different precision, different sensitivity. We'll still look at that as we go on. So depending on the level of precision and sensitivity you require in whatever you want to measure can also determine how you select or what kind of sensor you select in such an application. Also, we have what we call the dynamic range. We'll talk about that later. The level of automation also will determine the number of sensors that you might use. Also, the complexity, of the control system and the modeling requirements will also determine the selection of sensor that you might want to use. The cost, the size, and the usage and the ease of maintenance also are some other things that you might want to consider when you are selecting sensors. So for every modern control system, there are two very important elements in them, which is the sensors and transducer. So what the sensor does is to, detect the measurand. The measurand here is the variable to be measured, either temperature, pressure, whatever it's to be measured. That's what we call the measurand. And it converts them into acceptable form, generally as electrical signals. What I've explained earlier, that your sensor detects the magnitude of the physical parameter, changes it into electrical signal, either voltage or current, as the case might be for the sensor design. So the maximum accuracy of the total system, in this case a control system, is being controlled by the sensitivity of the individual sensors, and the internally generated noise of the sensor itself. By now you should know what noise is. When you have signals that are fluctuating, every sensor have its own noise. So if you are using any sensor on any control system, the maximum accuracy of that control system, is controlled by the sensitivity of individual sensors that you have used on that very system and the internally generated noise or noises of each of the sensors that you might have used on that very system. So figure 1.1, let me just move to that page. This is figure 1.1, it shows a mechatronics measurement system with auxiliary energy source. So we have the energy source here. This is the auxiliary energy source in this case. So we have the source. So the sensor detector is here, detects whatever is coming from this source. So from there it goes to the signal conditioner, and also whatever is being conditioned is being displayed, and that is being sent to the feedback sensor, and also that goes back to the source. The feedback sensor in this case is checking what is being measured here as against the set point, kind of a closed loop system. So just an explanation to that very figure is what we are trying to do here. So the function of the sensor is to sense the information of interest. So whatever information of interest that we have, the sensor senses that and converts it into an information that is acceptable by the signal conditioner. So the function of your signal conditioner is to accept that signal from the detector here and modify it into an acceptable form for the display unit, so that it can be displayed at the display unit here, so that a human being can understand what is being measured. So the function of the display readout is to accept the signal from the signal conditioner and present it in a displayable version, so that the human that's observing the output can understand what is being measured. So the output can now be in form of probably an output display. It can be a printed output, or it can be also passed into a controller. When you have a closed loop arrangement, whatever is being measured can be passed into a controller that can now check the system output as against the set point of the system, to see if there's any difference there, and the controller now can modify that signal to ensure that what is being desired is what is being presented at the output, depending on the arrangement of such system. Also here we have figure 1.2, which is showing us the general instrumentation system and its components. So this is an instrumentation system and the components. So we have different physical parameters: displacement, force, weight, temperature, pressure, flow, and digital. So and all of this can be sensed by a sensor transducer, and the signals can be processed, and you have an input and output structure to whatever application you want to apply it to. So I'm just saying here that figure 1.2 present the component of an instrumentation system used for a general sensing application. So you have the primary elements that senses and converts information into a more suitable form, which is just your sensor transducer here, to be handled by the measurement system. So the signal conditioning stage for processing and modifying information, and you have an input-output stage for the interface where you have the application here. So that is just the explanation of this general instrumentation system and its components. So we'll be looking at the sensor categories. Sensors are classified into two categories based on the output signal and the power supply. So what we're saying is that for sensors, we have two categories of sensors. And category A is the output signal category of sensors, and category B is the power supply category of sensors. Then we have the operating mode and the variables being measured. So what we are saying here is that based on these four factors, output signal, power supply, operating mode, the variable being measured, sensors can be classified broadly into two categories. So the first one we're looking at is the analog sensors. So, but before we go into analog sensors, let's look at table 1.1. So this is table 1.1, and this table is showing us classification of sensors and the sensor type. So when we're talking about signal characteristics, we're talking about analog and digital sensor type. So the signal, from a sensor can be analog or digital. When we're talking about the power supply classification, we are looking at either active or passive type of sensor. When we're looking at the mode of operation, it can either be a null type sensor or a deflection type sensor. Then when we're looking at subjects of measurement, or what is to be measured, or the variable being measured, it can be either acoustic, biological, chemical, electric, it can be mechanical, optical, radiation, thermal, or other kind of variables to be measured. So let's look at what analog sensors are. So the word analog is a term that is being used to convey the meaning of a continuous, uninterrupted, and unbroken series of events. So when we're talking about something that is analog, we're saying that that event is continuous, is a continuous, uninterrupted series of events. For instance, now your vehicle, when you rev your vehicle, if you look at the revolution dial on your instrumentation panel of your vehicle, you see that the revolution just keep increasing, in that manner. Those are analog signal in nature. They are continuous, they are uninterrupted series of events. So analog sensors typically have an output which is proportional to the variable being measured. So if you look at your vehicle revolution dial on the instrumentation panel, you notice that the more you throttle your vehicle, the more the revolution increase. So in that case, that is an analog kind of arrangement type of sensor, in that the output of your sensor, which is an analog sensor now, is proportional to the variable being measured. So any change in the variable being measured, is equally proportional to the change in the output that is being presented by the analog sensor. So the analog sensor output changes in a continuous way, just like your vehicle speed increases from 0 to 100 as you begin to travel or whatever it is. You see that your speedometer, continues to increase, and that's the output of your analog sensor in that case. So that continues to change, in a continuous way, and its information is obtained on the basis of amplitude for your analog type of sensor. So for every analog sensor, the output is normally supplied to the computer using an analog to digital converter. In the case of analog sensor outputs, the output cannot be, sent directly to a computer to process, because computers only process digital signals. So when you have an analog output, that analog output has to be sent, through a analog to digital converter to convert the analog output into a digital output that the computer can understand. Then we have digital sensors. Digital sensors are type of sensors. So before we look at that, we have to talk about what digital means. So when we say something is digital, it refers to a sequence of discrete events. When we say an event is discrete, we are saying that event A and event B are separable. You can separate event A from event B, unlike this series of events that you have in analog. You have a sequence of discrete events that can be separated from one another. So each event is separate from the previous and the next event. So they are separate events. In this case, that's what we mean by digital. So sensors are digital if such a sensor have what we call logic level outputs. So sensors that have logic level outputs are referred to as digital sensors. For instance, let's use your phone battery level meter, as an example. You have on your phone, what you see is your battery bar. Maybe 4 bar means your battery is full, 1 bar means your battery is low. 1 bar, 2 bar, 3 bar, 4 bar. 4 bars, represent different logic levels that sensor has, being able to classify your battery charge level into. So when it's 1 bar, it means probably the battery voltage level is maybe 20%. When it's 2 bars, maybe 40 or 50%. 3 bars, maybe 60 or 70%. And 4 bars, maybe 100%. So those bars are different logic level outputs, that your digital sensor that has been used in your phone has been able to categorize your battery levels into. So that is just a simple example of a digital output sensor type. So digital sensors, they are known for their accuracy and precision. They are more accurate and more precise compared to your analog sensors, and they do not require any converter, to interface them with a computer monitoring system. So, in the case of analog, you need to interface your analog output, through an analog to digital converter before you can send it into a computer monitoring system. But in case of your digital sensor outputs, so far the outputs already in digital form. You don't need to have a converter interface it with your computer monitoring system. So another form of classification is the active or passive, based on the power supply. So for your passive and active sensors, active sensors are sensors that emit energy, and they now measure the reflected signal in their own case. So let me just give an example so that we understand this kind of sensors. For instance, I don't know if you have worked with your ultrasonic sensors before. Ultrasonic sensor is used to measure distance between an object and the body that is carrying the ultrasonic sensors. Is used for collision detection in most cases, or your IR sensor, infrared sensor in this case. Those kind of sensors, they emit energy. Your ultrasonic in his own case sends a signal. When the sensor is powered, it sends out a signal. So until that signal strikes a surface, when that signal strikes a surface, then that signal is being reflected back to the ultrasonic sensor. So it's that reflection that the ultrasonic sensor now measures to determine the distance between itself and that object that reflected that signal back to it. So for active sensors, they emit energy into the environment. For example, your ultrasonic sensor, your infrared sensor, there will be an infrared light that will be lit when you put on your ultrasonic sensor. So when there is a blockage of that uh, light, then the sensor knows, okay, there's an object there that has been detected. So they emit energy into the environment and they measure the reflected signal. In their own case, those are active sensors. For passive sensors, in their own case, what they do is they actually measure the radiation, you know, from the target body in his own case. For example, your temperature sensor now. Your temperature sensor does not emit any energy into the environment, but what your temperature sensor does is to measure the radiation of heat from the body to which it wants to measure the temperature from, you know. So that is why they are called passive. In their own case, they measure the radiation from the body, you know, that they want to measure, whatever parameter they want to measure from. While active sensors, they measure the reflection, you know, the reflected signal to themselves after they have emitted energy into the environment. So they measure the reflected signal to themselves, and that's why they are called active and passive sensors. Also, we have what we call the deflection sensors and the null sensors. Based on the operating and display mode of an instrumentation system, a sensor can be classified as deflection type or null type of sensors. So if you are looking at the operating and display mode of an instrumentation system, the sensor can be classified into deflection sensor or null sensors. So these two types of sensors are used in instrumentation systems where we need to do measurements, particularly calibration measurements. So for your deflection sensors, they are used in a physical setup where the output is proportional to the measured quantity that is displayed. For instance, the measurement of weight or mass, you know, can be read, you know, via a dial when you put the mass or the weight on the sensor. So the deflection sensor, they are used in physical setups where the output is proportional to the measured quantity that is displayed. But for your null sensors or zero sensors, they are more accurate than your deflection sensors. So when you need high accuracy measurement, that is when you'll be using a zero or a null sensor type. And in their own case, any deflection due to the measured quantity is being balanced out by the opposing calibrated force so that any imbalance is detected. So what are we saying in this kind of sensor? So you have a sensor that is used to measure a certain quantity, but you have an opposing force, like you have a counterbalance, so that whenever there's an imbalance, when the sensor measures something, the counterbalance now is used to determine what is being measured. That okay, what this change in this sensor, how much opposing force was used to turn it to zero. So that opposing force that is being used to turn it to zero is now the measured value of whatever it is that you have used your null sensor to measure. One example that we can use for your zero null effect sensor so that we can understand is, I don't know if you have gone to the maybe to building equipment store to buy nails, and you want to buy probably 1 kilo of nail. What they will just do is, you have this mass, you know, that has 2 pans. They put the nail on one pan and they begin to put the weight on the other side. You know, when they put the nail on one part of on one of the pan, there will be a deflection, you know. Then they begin to put the mass, maybe 1 kilo, 0.5 kilo on the other side until the displacement, becomes balanced and it balance out. So they now tell you, okay, that is 1 kilo of nail. That is a type of null effect kind of sensor, just like something like this. When you have all uh the unknown mass, you just pack the nails, you put them on this side, and you begin to put the maybe 0.5 kilo, 1 kilo mass on the other side until you have a balance of the two pans, and whatever you now read here, is now the mass or the weight of your nail that you are buying. So that is what a null effect kind of sensor arrangement is all about. So the final classification of sensor is based on the subject to be measured, and the subject to be measured is a wide range of subjects. It can be acoustic, it can be biological, it can be chemical, electric, it can be magnetic, it can be mechanical, radiation, thermal, and all that type of subjects to be measured. So that takes us to the next subtopic, which is the parameter measurement in sensors and transducers. So figure 1.3 shows the block diagram of the elements of a typical instrumentation system, and it consists of your sensing module, conversion module, vibration manipulation module, the data transmission, the presentation module. So this is what your element of an instrumentation system looks like. The measured medium is here. So you have the sensing module. The sensing module senses the measured medium, maybe temperature, pressure, whatever that is. So the sensing module senses that. After whatever is to be sensed has been sensed, then you have your conversion module, which converts whatever is being sensed, and you have your variable manipulation module. Then that goes to your data transmission, then your data display, then you have the human observer to see what has been measured. So what was your sensor module? What does it do? So the first element to receive a signal from the measured medium, just from the figure that you can see, is the sensor module. And what it does is to produce an output depending on the measured quantity. So the sensor module here produces an output that depends on this measured quantity, and the output of this is being picked up by the conversion module. So what conversion module does, is to convert one physical variable, to another, and it is known as a transducing or the transducer or the transducing element. So we have been talking about sensors and transducers. So this conversion module here is the transducing element. So the sensor senses, the transducer converts it into a signal that the system can process. Then we have the variable manipulation module. Usually that involves what we call signal conditioning. Some example of that variable manipulation elements are your amplifiers, your linkage mechanism, gearbox, amplifiers and magnifiers, and what have you. So those are your variable manipulation module. So for instance, now an electronic amplifier accepts a small voltage, and converts that small voltage, which is the input signal in this case, and generates a signal that is many times larger than the input signal. So just by the name amplifier, it amplifies the inputs. So your variable manipulation module can be an amplifier, it can be a magnifier, it can be a gearbox, it can be a linkage mechanism. What they do is to receive the signal at some level and increase it as many ratio as they are being designed to do. Then we have the data transmission module. What data transmission module here does is to send signal from one point to another. That's what the data transmission module, that's what it does. For example, you have your transmission element, could be a simple device such as your shaft, can be a bearing assembly, or could be any other complicated device that can be used to transmit such signal. Then we have the display module. Your display module is just to produce information about the measured quantity in a form that can be recognized by an human observer. So your display, your data display module here, presents whatever is being measured and transmitted into a form that the human observer can comprehend. That is what the module does. So an example here is just an home meeting system whereby we have a temperature set point of 60, 50, and 70. So we have the temperature sensor here reading whatever temperature value is from probably the heating element in this case, and also there's a set point that this should be. So what happens is you have a relay here. This relay controls the fuel pump or the igniter that initiate the burner to burn, so that the radiator can increase temperature and the room temperature can also be increased. And whatever increase that is being measured in the room temperature is being checked against the set point. So when the temperature set point and the room temperature, which is being sensed by the temperature sensor, are equal, then the relay that controls the fuel pump and the igniter for the burner to burn will not open, so that the temperature will be maintained. But as the temperature begins to drop, this relay now opens to allow the fuel pump and the igniter to engage, so that the burner can start up again and the radiator temperature can increase and the room temperature also will increase accordingly, and that cycle goes on. That's just an example of an instrumentation system in that wise. Also here you have a pressure sensor illustration whereby you have a pressure source, you have a piston cylinder, and you have the display. Now we know that as your pressure increases, your volume will reduce and vice versa. So as your pressure increases, your piston displacement will increase, which will cause a display accordingly. And when there's a reverse also, the piston length or the displacement will reduce and the force also will reduce. This is just a schematic diagram of a pressure sensor of this kind of arrangement. When you have a pressure source, you have a piston cylinder, and you have a display unit. Now, for every sensor, we have what we call the quality parameter of sensors and transducers. And those quality parameters are sensitivity, resolution, accuracy, precision, backlash, repeatability, and linearity. Now, sensors and transducers are often used, under different environmental conditions. Like for us human beings, we have different kind of environment that we can be in, and our bodies are designed to sense temperature of our environment or touch or whatever it is that is around us. So the same way too, sensors do that. So for every sensor, the quality of that sensor can be decided by its sensitivity, the resolution, the accuracy, the precision, the backlash, the repeatability, and linearity of that sensor. So what do we mean by a sensor's sensitivity? We're saying that the property of the measuring instrument, which is the sensor in this case, to respond to change in the measured quantity. So the more sensitive a sensor is, the quicker it can sense changes, in the measured quantity. That is about sensitivity. Now you want to have a sensor that is very sensitive, so that any little change in your measurand, the sensor can pick it up. And your sensitivity also is expressed as a ratio of change in output to change in input, which is what you have, in figures 1.6 and 1.7 here. So you have your transducer, you have your input, you have your output, you have the energy source. So the ratio of change in output to input is your sensitivity, which is being also replicated with this graph where you have change in output and change in inputs on your y-axis. So your sensitivity is measured, like we already established, as change in output over change in input in this case. So by way of example, let's assume that we have an electrical measuring instrument, and if a movement of 0.001 mm causes an output voltage change of 0.02 volts, we already established that sensors convert physical parameters into electrical signals, majorly voltage levels. So the output you'll be having in most cases are voltage changes. So in this case now, we have an electrical measuring instrument that senses a change of 0.001 mm, and that change causes an output change in voltage of 0.02 volts. So if you want to measure the sensitivity of such a sensor, it's just 0.02 divided by 0.001, and you have your sensitivity output for that sensor as 20 volts per mm. So that is just a simple example of your sensitivity. Then we have what we call resolution. What do we mean by resolution of a sensor? The resolution is defined as the smallest increment in the measured value that can be detected. So what we're talking about resolution is this: what is the smallest increment in your measurand that your sensor can detect? What is the smallest increment in your measurand that your sensor can detect? That is the resolution of that very sensor. Sometimes they also refer to it as degree of fitness with which measurements can be made. For instance, if you have a micrometer with a minimum graduation of 1 mm and is being used to measure to the nearest 0.5 mm, then you're saying that the resolution of that very micrometer is 0.5 mm. You're saying that that is the smallest increment that micrometer can pick up. That is what we call resolution. Then also we have accuracy. Accuracy of a sensor is measured as the difference between the measured value and the actual value. These sensors are actually measuring physical parameters. For instance, now let me say I have a multimeter and I have a voltage sensor, in a circuit. The voltage sensor is sensing the voltage and giving me the output. However, I can use the multimeter also to measure manually and confirm if the multimeter is saying 2 volts and the voltage sensor is saying 1.5. So the accuracy of my voltage sensor now is the percentage difference, of the measured value, which is the value from the voltage sensor, minus that of the multimeter value, which is the true value, divided by the multimeter value times 100. That is the accuracy of that very sensor, just by way of explanation in that sense. Then we also have precision. We also have precision, and your precision is the ability of an instrument to reproduce a certain set of readings within a given accuracy. What are we saying here? So when we say precision, for instance, I have a sensor that is being used to measure voltage, like a voltage sensor. If I use that same sensor to measure the same voltage. Maybe I know the voltage of this system is 2 volts, and I use that same sensor to measure that 2 volts repeatedly. It should be able to give me outputs that will be within a given accuracy. Maybe 80% accuracy or 90% accuracy. If I use it to measure the same thing repeatedly, maybe I use it to measure the same 2 volts 10 times, you should be able to give me, a precision that will be within a range of accuracy. That will not give me probably measure 2 volts now. The next time it measures 1.5. Another time it measures it at 1.8. Another time it measures it at 1.2. That is not an accurate kind of sensor. You should be able to give me, reproduce that reading within a given accuracy, maybe an accuracy of 80%. So that when it measures it as 2 this time, it measures it at probably 1.9 the other time. Another time it measures it at probably 1.99 or 1.95. So it gives me within an accuracy. That makes that sensor reliable. Because if the precision of a sensor is not within a given accuracy, then that means that sensor is not a reliable kind of sensor. So the other quantity is backlash. Backlash has to do with mechanical measurement systems, and backlash are just movements that are not registered. So when you have a mechanical measuring instrument, for mechanical they move. So backlash is defined as the maximum distance or angle through which any part of a mechanical system can be moved in one direction without causing any motion of the attached part. So the attached part in this case is the sensing device on that mechanical measuring instrumentation system. So the backlash in this case is the maximum distance that the mechanical end of it will move and will not cause any motion that can be detected by the attached sensing device on it. So that is why backlash is an undesirable phenomenon, and it is important when it comes to precision design. Of gear trains, because you don't want backlash at all, because backlash are movements that goes on unregistered. So when you are even having it in a mechanical instrumentation system, there are movements that will occur and the sensing elements will not detect such movement. So you don't want any backlash in your mechanical instrumentation system. Then we have what we call repeatability. Repeatability has to do with the ability of a sensor to reproduce the same output signal exactly when the same measurement is applied repeatedly under the same environmental conditions. So what are we saying here? If I have a sensor and I want to use that sensor to measure the same signal, the same signal under the same environmental condition, I want that sensor to give me the same output, repeatedly. The same output in this case is different from precision. Now, the same output, if the output is 1 and I expose that sensor to that same measurand, which I know that the output should be 1, I expose the sensor to it repeatedly under the same environmental condition, the sensor should be able to give me 1 every time I expose it to that measurand. That is what we call repeatability. Then also we have what we call linearity, which is the final quality parameter of a sensor that we are going to be discussing. So linearity talks about the outputs from your precision instruments. By default, the idea is that the output from your measuring instruments, is linear to the input, but in real life, the output from your measuring instruments are not actually linear to the input. There's always, some level of deviation from the linearity of the input. So the deviation from the linearity that should be there, between the outputs that the precision instrument is reading out and the inputs being measured, that difference in their linearity, is what is termed as the linearity tolerance. So the linearity of every sensor is expressed as the percentage of departure from the linear value. So let's say now a certain input is 1, which the output actually should be 1, but your sensor will be reading out probably 1.1 or probably 1.01. That 0.01 is the linearity tolerance, and the percentage of it, the linearity now is being expressed as the percentage of departure from the linear value that should actually be read out from your sensor. So the next topic we'll be looking at is what we refer to as actuating devices. So these are just devices that cause motion or some action to happen, and most mechatronic systems involves motion or action of some sort. So based on that, they require actuating systems or actuating devices. So the motion or action can be applied to anything from just a single atom to a large articulated structure, as the case might be. What the actuator does is to create a force or a torque that results into acceleration or displacement of a body in the system or the environment. So actuators basically are devices that produce motion or actions, and there are several types of these kind of systems. You can have the solenoid type, you can have the electric motor types, you can have the hydraulic type of actuating systems, you can have the rotary motors or the pneumatic cylinder type of actuating devices. So whichever of them, either the solenoid, the electric motor type, the hydraulic cylinder type, the rotary motor types, or the pneumatic type, what they do is to produce motion. And an actuator in itself is very important to mechatronic system design, and to that extent their selection is very important, because whenever you need motion or some action to take place, particularly mechanical actions to take place in a mechatronic system, you need to select the appropriate actuating device. And when it comes to selection of actuating devices, there are 4 major factors that one must consider. Number 1 is the precision, and also you have the accuracy and resolution of the actuating device, the power required by the actuation for the actuation, and also the cost of the actuation device. So these are the 4 main factors that you need to consider when you want to select an actuator for a certain mechatronics design purpose. And the most popular actuator that you can have in mechatronic system is a DC motor, which is direct current motor. And also the DC motor actuators predate the AC motors. They are the first kind of actuators that are being used in system designs. So DC motors are electromechanical. They have the electrical side and the mechanical side. So the electromechanical devices that provide precise and continuous control of speed over a wide range of operations by just varying the voltage applied to the motor. So what we're saying is that for your DC kind of actuators, you can have various speed, or you can control the speed by just varying the voltage across the motor. And the desirable features of your DC motor are their high torque, speed control ability over a wide range, speed to torque characteristics, and their usefulness in various type of control applications. So those are the major desirable characteristics of your DC motor. That is why you find them most commonly used in your mechatronic system designs. So, and also your DC motors are well suited for many applications, including manufacturing equipment, computer and numerical control systems, servo valve actuators, tape transport mechanisms, and also industrial robots. And what they do basically is to convert direct current electrical energy into rotary mechanical energy. And they use the principle that a wire carrying a current in a magnetic field experiences a force. That's the principle they use. So you have the electrical side, which consists of the armature. The armature is divided into two. You have the rotor and the stator. The rotating member of the armature is called the rotor, while the winding field is the stationary winding, which is called the stator. So the rotor has many closely placed slots on this periphery. So here, so that we don't bore ourselves much with too many electrical terms, here you have the conventional DC motor diagram and the loading. That's what is being shown here in your figure 1.8. This is the conventional DC motor diagram, and this is the loading diagram of it. So you have the electrical side, and you have the shafts, which would, at the end of the day, rotate once you have powered your electrical side, and you have the torque and the angular velocity on the shaft on which you are going to attach the load. Then you have a damping on your electrical side, which is denoted by your capital letter B. And this is the loading, whereby you have a voltage VM across your armature, and your voltage, you have your voltage VM, which is your input voltage, and there will be voltage drop across your RL circuit, which is the armature. Your VM is applied to your armature, and that voltage will drop across this RL circuit, and your V here is your voltage over your motor itself, and this is the load here, and this is the angular velocity omega. So the mathematical model of your DC motor, there are two mathematical models that explains the fundamental behavior of a DC motor. That's your torque equation and the voltage equation. For your torque equation, you have your T equals KTI, and your voltage equation, you have your V equals KE theta. So your T is the motor torque in Newton meters, your V is the induced voltage in volts, your I is the current in the armature circuit in amperes, and your theta is the rotational displacement of the motor shaft in radians, while your KT is the torque constant in Newton meter per amperes, and you have your KE, which is the voltage constant in volts per rads per second. So when your VM, when an input voltage is applied, your VM is applied across the armature, while the voltage equation is influenced by the drop in the voltage across the RL circuit here. And you have this VM equals RAI plus L subscript A di dt plus V. So when your VM is the voltage applied to the armature terminal in volts, your RA is the armature resistance in ohms, your LA is the armature inductance in Henry, and your I is the armature current in amperes. Now, that is the electrical side. For the mechanical side, this DC servo motor derives a mechanical load, which consists of dynamic and static components. So the primary load on your motor are the inertial and the friction, and the varying torque is represented by this equation here. You have your T equals J theta, second derivative of your theta, plus B, second derivative of your theta, plus TL, while your J is the moment of inertia of the rotor, your B is the viscous damping coefficient, and the TL is the load on the motor. So the DC motor is capable of producing high rotational velocities and comparatively low torque. Now, because we might need to make some adjustments on the rotational velocity and the torque of your DC motor. There's always the need for a gearing arrangement, because when you are using your DC motor as an actuator, there's always a need that you might want to vary the rotational velocity against the torque. So based on that, you need a gearing arrangement to vary the torque against the speed, because your DC motor provides a torque which is proportional to the armature current. So for you to, if the armature current is constant and yet you want to vary the torque, then you need a gearing arrangement at the output shaft of your DC motor to vary the torque, so that once your torque increases, your speed will reduce, and vice versa. So the next topic we'll be looking at is your system control logic methods. So your system control logic method is just a method by which a control system makes decisions based on their inputs. So these are a set of techniques used to design the decision-making process within a control system. So when you have a control system, how would that control system make decisions? So they make decisions based on the control logic method technique that has been designed in them. I will have several of them, which I'm going to be discussing as we go on. So the first is your sequential logic, which is the method that relies on a predefined sequence of steps to be executed one after the other. So in this sequential logic now, you have several steps that a control system must go through to get to the final decision, just like you have in a flowchart. For instance, your domestic automatic washing machine, once you load in your fabrics and you shut the door, the first thing that will happen when you put it on and you select your washing cycle is for the sensor to detect if the door is closed. So once the door is closed, then it brings in water, and also there is a sensor that checks if the water is actually coming in. If the drum is not filling up as it should be, then that means the water is not coming in. It will probably come out with an error, but if the water is coming in at some point, it will check the weight of the drum as against the initial weight to tell, okay, the water is enough, so it will stop the inlet valve, and then your washing cycle will commence. After your washing cycle, it drains the water, it brings in fresh water for the rinsing cycle, then it goes to the spinning cycle again. And if it's a drying, it's a washing, spinning, and drying washing type of machine, it equally dries before it ends the cycle. So if you look at that, that's a sequence kind of logic. After this, you do this, you do this, you do this, you do this. That's a sequence kind of logic in that sense. Then also we have the state machine logic. Think of it like a traffic light control system, whereby you have green, red, and yellow. Your green is a state, your yellow is a state, your red is a state. And each of these states have different actions attached to them. For your red, that means stop. Your yellow means ready, while your green means go. Go. So this state machine logic, this method involves the system transitioning between different states based on input signals. So, and each of these states, like I said, have associated actions with it. For instance, the input to your traffic light might be a sensor that is sensing the change in traffic flow, or just a timer that specify when the duration for red is over, the duration for yellow is over, then the duration of green is over, and in that sense. Then also we have the decision tree control logic method, whereby you have a tree-like control logic where the branches represent decision based on specific conditions. These systems follows the path based on the results of these conditions. An example of that is your thermostat cooling system, which can be in a room, whereby you want to have a certain temperature in a room, and you set the set point of your thermostat to that very value of temperature, and you have an heat generator, in that room, maybe an heater or whatever that is, and the temperature sensor is checking the temperature of the room and reporting that into the controller. And once the set point is attained, then the controller sends a signal to your heat generator to stop heating the room. That is a kind of decision tree logic method. Then also we have the fuzzy logic. We use fuzzy logic, control logic method when the input that we are dealing with is subjective, when the input is an imprecise input. For instance, temperature is an imprecise input, whereby, for temperature, you cannot go from temperature 0 to 100. You go from 0 to 1 to 2 to 3 to 4 up until 100. So that you can have cold, you can have warm, you can have slightly hot, you can have hot, you can have very hot, and you can have extremely hot. Those are subjective states that your system can be in. So based on that, we can use fuzzy logic to, model these states in different membership functions so that we can monitor them appropriately. So just like a temperature control system in a car, we might use fuzzy logic to adjust the air conditioning based on passenger comfort level instead of just relying on solely the specific temperature settings, so just something like that. Then we have the rule-based system type of control logic method, whereby the system makes decisions based on some predefined set of rules. For instance, we have the something like a fraud detection system. If you use ATM machine very well, or even your phone banking app, if you input your password 3 times incorrectly, you see that account will be blocked. Or if you do it on an ATM machine, you see that the ATM would seize that card. So what they have done in that case is to use a rule-based control logic method to say that, okay, if a password is entered 3 times in successions, then it's a fraudulent transaction. That is just a practical example of your rule-based type of control logic that has been used in real-world application. So that takes us to introduction to signals, system, and controls. Now, these 3 words, signals, systems, and controls, you find them majorly in mechatronic systems, and we need to understand what they are because they are interrelated. So what are systems? Systems are plants. Some cases they refer to them as plants, some systems, so you need to be aware of these 2 words. So systems are either naturally occurring, maybe a God created system, or a man-made entity which transforms inputs into outputs. So anything that changes an input into another output, then that thing is a system or a plant. For instance, your DC motor is a system in the sense that the input is electrical signal and the output is a mechanical signal. It's a mechanical output. So that is a system by itself. So a system can either be God created or man created system. Now, we might need to modify the behavior of a system. Like we explained when we were talking about DC motor. You have the output. The torque output of a DC motor depends solely on the voltage or the current across the armature. But in application, we need to, modify the torque against the speed. Then we need to attach a gear to it. So when we need to modify the behavior of a system, we would have to do what we call control. So whenever we are modifying the behavior of a system, then we are doing what we call control. And for us to do a control to modify any system behavior, we need to implement either a controller or a compensator. We need to attach either a controller or a compensator to that system or to that plant for us to modify its behavior. And whenever we attach a controller or a compensator to a system or a plant, then that combination is referred to as control system. Now, control system incorporates either human or machine controllers. A system converts an input into an output. To modify the behavior of a system, you need to do control. For you to do a control on a system, you need to attach that system with a controller or a compensator. And when you attach a controller or a compensator to a system, you have a control system. And your control, your controller in this case can either be a human or a machine controller. When it's a machine-based controller, then you have what we call automatic control. Now, for any control system, we have what we call variables and functions. So, for every control system, we have variables and functions. Now, we have two types of variables. Variable can either be a constant variable or a varying variable with respect to some independent variable, in most cases, time. So, the constant variables are referred to as parameters, while the varying variables are referred to as signals. So that is where the three words come from: signals, systems, and control. Let me just run over it again. System converts input to output. To control the behavior of your system, you need to do what we call control. For you to do a control on a system, you need to combine that system with either a controller or a compensator. And once you combine a controller or a compensator to a system, you have a control system. And the form of control that you are doing can either be human-based controller or a machine-based controller. When it's a machine-based controller, you have what we call the automatic control. And for every control system, we have variables and functions. Variables can either be constant variables, which are referred to as parameters, or varying variable with respect to some independent variable, basically time in most cases, which are referred to as signals. So signals, because they are variable, they change with respect to an independent variable, usually time. And the behavior of a signal is often considered in two regions. For every signal, you consider their behavior within two regions, which is the transient region and the steady state region. For the transient region of a signal behavior, in that region, the signal derivatives dominate the shape of that signal, while in the steady state region, all the signal derivatives die out, leaving only the DC offset value, which is being sent to that very system. So this is what figure 1.13 is trying to show. We have a certain signal x of t sent into a system, and from this legend here, input, output. So this is your input, while this is your output, and from here, the starting point of this signal behavior up until where the signal begins to settle down here is referred to as your transient region, while from here to where the signal has actually settled down here is referred to as your steady state region. So this is where the derivative of the signal dominate the shape of that signal, and this is the region where the derivative has already died out, and only the DC value forms the shape of your signal behavior in this case. So there are different regions of your signal behaviors. One of them is your rise time. The rise time is the amount of time the system takes to go from 10 to 90% of the steady state value. So the rise time of this signal is the time it takes it to go from 10 to 90% of the steady state value. The steady state value of this signal is here. So the amount of time it takes this signal to go from 10 to 90% of this value is what it is referred to as the rise time of that signal. Then also we have what we call overshoot. This is what we see here. So the overshoot of your signal is the difference between the highest peak of your signal to the input signal to the system. This is the output. This is the input. So the difference between the highest peak of that signal to the input to the system is referred to as your overshoot, and the percent overshoot, PO, is the amount that the process variable overshoots the final value, expressed as a percentage of the final value. And the mathematical model is shown here, which is 100E. The error here is just the difference between these 2 points. The damping factor, your length, pi, square root of your 1 minus the damping factor, damping ratio, square of that. So also we have the steady state error, ESS. The steady state error is the final difference between the process variable and the set point. Now the input here is the set point. The input is the set point. So the final difference between the process variable and the set point is referred to as your steady state error. So the difference between this output and this input at this endpoint here is the steady state error. Then also what we'll call the settling time, TS. The time required for the process variable to settle to within a certain percentage, commonly 5% of the final value. The time it takes the process variable to settle within 5% of the final value. That is what we'll call the settling time. Then also the model is TS equals log ESS divided by your damping ratio and your WN, which is your natural frequency. So the next we want to discuss 2 things which are shown in your tables 1.2 and 1.3. Table 1.2 shows the 4 basic control signals in a control system, while your table 1.3 shows the 4 basic control system function. 1.2 shows your 4 basic control system signals, and 1.3 shows your 4 basic control system functions. So for your control system signals, there are 4 types of signals. We have your reference or command or your set point signal. Like in the example of the room temperature that I explained, you set the temperature you want the room to be in. That temperature you set for the room to be in is your reference or the command or the set point signal, which it is introduced externally. It's an external input, and it's sent to the controller, and the variable to represent your reference or set point signal is your R of t or y second derivative of t. Then we have the control signals. The control signals is the input signal created by the controller and provided to the plant. So the output of your controller that is being sent to your plant or your system is your control signals, and the variable representing that one is u of t. Then we have your controlled signal. The controlled signal is the signal from your plant or your system. That is the controlled signal, and the variable used to represent that one is your y of t. Then we have the disturbance signal. These are noise in your system or in the sensor, and it's being represented by d of t or w of t. Then for the 4 basic control system functions, there are 4 of them. We have the compensator or the controller, the process plant or uncontrolled system, the sensors and actuator or drive. So the four basic control system functions. The compensator or the controller, the function of the controller in this case is the controller is attached to your plant through sensors and actuators, and what they do is to modify the performance of your system or your plant. That's what the controller does, or your compensator, to modify the performance of your system or your plant. And the typical variable for that is your C of S or GC of S. They also have the process or the plant or the uncontrolled system. So this is just the system or process which is to be controlled, and that is being represented by your GS or your GP of S or your TS. And also we have sensors. Sensors are devices that convert physical quantities, either temperature, pressure, etc., into low power electrical signal capable of being read by your computer. And that is represented by your G sense of S. Then also we have the actuator or drive, which is a device which converts the low power command signal from your computer into a high power signal, which creates motion, heat, or pressure. And that is being denoted by your G act of S. So this diagram here is showing the general control system diagram. The R here is your set point signal, like we just discussed. Then your C of S is your controller or your compensator, and that controls your actuator. That's your G act of S. Then the signal from there is your control signal, which goes into your G of S, which is your plant. Then the plant noise adds to that signal, and the output of that is your Y, which is your controlled signal. And that same control signal is being evaluated by your sensor, which is your G sense of S. And the sensor noise also adds to that signal, which is being sent back to where you have the comparator here. The comparator here compares your set points and your controlled signal to see if there is a difference there. Where there is a difference, that difference is sent into the controller, and the controller compensates for that difference by sending a signal to the actuator to send a signal to the plant to make necessary adjustments. So this is a closed loop, and that cycle goes on and on and on like that. So in the next video, we'll be looking at the Laplace transform solution to ordinary differential equation. So thank you very much for listening.